Good morning, I'm Jose Armando Gastelo Roque. I'm a Peruvian student. I study at Pedro Ruiz Gallo National University in Peru. And this morning I'm going to tell you about a work that I did it in Mexico during a research stay in the Center for Research and Advanced Studies of IPM, the same staff. My work is called Design of a Photovoltaic System using Thermoelectric Peltier Cooling for Bathing Refrigeration. The present work aims to solve a community problem, a problem which we will tell about in a moment. Basically, my work consists in designing a cooling system to store vaccines, which use solar energy and thermoelectric effect. But why? Well, the vaccines are thermolable medicines, and the thermolable medicines are those that require specific conservation conditions, usually requiring low temperatures between 2 and 8 degrees. If these conditions are not satisfied, these medicines can deteriorate and lose therapeutic power. Therefore, it's necessary and obligatory to refrigerate the vaccines and other thermolable medicines. But the conventional cooling systems require connection to the electrical grids. The problem is when there is a lot of electricity in some communities. Because of this, the conventional cooling systems can't work, and it's not possible to store and refrigerate vaccines. This causes a series of problems, health problems, community problems, since people of this community don't have vaccines within their reach. This is a common problem in Latin America and in the world, but for this research, a study location has been taken for analysis purposes. The location selected was my city, Lambayeque, in Peru. Lambayeque is a city in the north of Peru that has many rural communities that don't have access to electricity. Our solution is a cooling system that uses solar energy, since solar energy is worldwide available, and will use thermoelectric cooling to be suitable for the application. The advantage of this system are first, solve a community problem. Use a renewable energy, in this case use solar energy, and this is important for the fight against climate change. It's not contaminant, it's without emission of polluting gases and without the noise and the maintenance typically associated to conventional refrigeration system. And the last one is totally sustainable and easy to replicate. Okay. Now let's see the arrangement of our system. It's composed of a PV module that is in charge of converting the energy that comes from the sun into electrical energy. It goes to a battery system where it's stored and then supplied with electricity to the refrigerator, where the thermoelectric cooler, the depth, transforms the electricity into heat, in this case in heat extraction, to be able to refrigerate vaccines. The graph below shows the flow of energy in the system. This starts as solar energy, the PV module transforms it into electrical energy, it's stored in the batteries, and finally reaches a step where it ends in form of heat. As we have seen, the fundamental device of our system is the thermoelectric cooler. And this is a device that directly transforms an electrical current into a difference of temperature, into heat. It uses a Peltier cell and is based on the Peltier effect. A TET is composed of a Peltier cell, and on its sides are placed cold and heat radiator. With these accessories, we have a device that can be easily and efficiently cooled. If we fit a properly insulated container on its cold side and we apply electrical current, you get a better technology than vapor compression refrigeration or other conventional refrigeration systems. The primary advantage of a thermoelectric cooler compared to other refrigeration systems are its lack of moving parts or circulating liquid, very long life, invulnerability to leaks, small size and flexible shape. Well, to design this system was followed a specific methodology, and some consideration for the design were taken into account. Regarding the methodology, first we calculate the thermal load of the system, that is to say the heat that we must extract to maintain the temperature conditions inside the refrigerator. Later, the thermoelectric system is designed, the TET to be used, the thermostat and other control devices are selected. Then, we proceed to the dimension of the photovoltaic module, where we find the quantity and type of module to be used to satisfy the energy demand of the system. And finally, the battery system is dimensioned, where the energy will be stored. With regard to design consideration, first, there are several types of vaccine presentations. There are the single dose and the multi-dose. In this work, it's considered that the vaccines to be stored are vials multi-dose. In accordance with the information provided by the Health Ministry in Mexico, for a health center in rural towns, the minimum amount of indispensable vaccines is 5 liters, so the capacity of this refrigerator is 5 liters. We consider that the ambient conditions such as temperature, radiation, humidity, and so on were those at Lambayeque, Peru, but can be easily adapted to other places of the world. Since the vaccines must be stored between 2 and 8 Celsius degrees, we consider that the average temperature in the refrigerator is 4 Celsius degrees. For the thermodynamic analysis, we consider the vaccines with the properties of water. Okay, the thermal load is the heat that must be extracted to the refrigerator to maintain a suitable temperature inside it. In this case, we must maintain a temperature between 2 and 8 Celsius degrees. The total thermal load is determined by this expression. Total thermal load is equals to load of the product plus transmission load plus intermission load. The load of the product is the heat that must be extracted from the product, in this case from the vaccines, to take it from an initial temperature to a final temperature. The transmission load is the heat that must be extracted to counteract the heat flowing from the outside to the inside through the wall of the refrigerator. The outside temperature heats the interior of the refrigerator, and that should be considered. Finally, each time the refrigerator is opened, a mass of air enters. This also raises the interior temperature, and to reduce this is considered the intermission load. Now, we must calculate each of them to obtain the total load. And using the formula of refrigeration handbook, the thermal loads obtained are these. We get 2 thermal loads, and this is because the room temperature is different in the day and at night. The total thermal load in day is around 22 watts, and at night is 16 watts. Since we have the thermal load, we proceed to select the convenient test for the system. For this, we have to take some considerations. First, the heat that must be extracted. We have 2 thermal loads, but we will take the thermal load of day. The thermal load of day is 22 watts. We will also consider that the temperature of cold side of depth is 5 degrees, and that the room temperature of Lambayeque, the average of room temperature, is around 29 degrees. With this consideration and following the procedure outlined by Tam and Fott, and using the universal performance curve proposed by Butz, we obtain the characteristic parameters of the depth. With this data, we can search in databases or catalogs the appropriate depth for the system. Find it that we need a test model 195 and with these characteristics. But we also need to know the operation parameter of the test in our system, such as the operating voltage, the power consumed, and so on. For this, we use the electric modeling formulas of Linekin and Jacob. And we obtain the operation parameters. The operating voltage is 12 volts. We chose 12 volts for being the voltage of the PV modules and the batteries. The power consumed is 37 watts, and the coefficient of performance is around 0.6. Now, a thermostat will be included in the cooling system. The thermostat will be in charge of connecting or disconnecting the electrical energy according to the temperature inside the refrigerator. We consider that the refrigerator will always be between 4 and 6 Celsius degrees. When the temperature inside reaches 4 degrees, the thermostat will disconnect the electrical power, and the refrigerator will enter in an unfreezing phase. When the temperature reaches 6 degrees, the thermostat will reconnect the electrical energy source, and the refrigerator will enter in a freezing phase. And it will repeat this cycle throughout the day. Assuming that each day the refrigerator works during 12 hours in the freezing phase, we can calculate the electrical energy consumed by the system, and this results in 450 watt-hour. Now, we have the power and energy consumed by the system, so we can proceed to dimension the photovoltaic module, which will be responsible for supplying power to the system. To size the module, we need to calculate the peak power of the module, and it's obtained by this expression, where HPE is the amount of equivalent peak hours in the location where the system is to be used. In this case, in Lambayeque, Peru. Replacing, we obtain that the peak power of the module is 92 watts. Now we can proceed to size the battery system. For this, we must calculate the capacity of the battery system, and that is determined by this expression. Here, we must know that we consider 3 days of autonomy. This means that if there is a solar source of the module of the system is disconnected, the system will be able to operate up to 3 days with the energy stored in the batteries. We obtain a capacity of 212 ampere hours. This is a representation of the refrigerator next to a diagram of the system. Finally, we can conclude that a thermoelectric cooling system that uses solar energy was designed to store vaccines in areas without electrical energy, for example, in Lambayeque, Peru. This refrigerator has a volume of 50 liters, but just 5 liters of vaccine storage capacity. It used a TED of 12 volts model TE195 with a power consumption of 37 watts. It used a PV module with a peak power of 92 watts, and the PV module is to be connected to 12 volt batteries with a capacity of 212 ampere hours and with 3 days of autonomy. We are currently developing the prototype of the system to validate the design described here and in search of financing to implement this system in rural areas. I want to end by taking my advisor, PhD Arturo Morales Acevedo, who is professor in Simvestat in Mexico, for the help and advice in this work, to the government of Mexico for the scholarship in which I could develop this work, and to my university in Peru, especially Dr. Ernesto Hashimoto, for his support in the presentation of this work. And that's all. Thank you very much.